My name is Iman Mondal. I am an assistant professor in the Indian Institute of Technology, Kanpur. In this presentation, I will be talking about the work on analysis and comparison of distortion of Miller and feed-forward op-amps in negative feedback. Op-amps in negative feedback are frequently used in integrated circuits to design buffers or for accurate amplification while driving large capacitive loads. Since these op-amps are realized using nonlinear transistors, their output response is also distorted. It is well known that when used in negative feedback, the distortion performance of the loop improves by the factor of the loop gain of the negative feedback loop. So, if the input signal has a certain bandwidth, we need to ensure that the loop bandwidth is larger than the bandwidth of the signal itself in order to keep the distortion in check. This obviously has few repercussions. For example, in a wireless receiver, the larger than necessary bandwidth can result in an out-of-band signal entering the signal chain. In a sampling system, this can also result in holding back of out-of-band noise. With this in mind, in this presentation, we will look into the distortion performance of two of the most commonly used op-amp architectures, namely the Miller and the feed-forward compensated op-amps. Before we launch into analyzing these, let us talk about the distortion model that we will use in this study. We will assume that the dominant source of distortion in the transconductors is the modulation of the transconductance itself, and will be modeled as shown in the figure, and we will neglect the distortion emanating from the modulation of the output conductances. Also, we will assume a fully differential implementation of the architectures and will neglect the even order non-idealities. Further, we will also assume a weakly nonlinear system and will limit our discussion to third order nonlinearities only. Now let us put this humble transconductor in a negative feedback loop to realize a closed loop gain of k-1. In order to intuitively analyze the effect of the distortion, we will resort to the analysis presented in the cited paper. Since we have made the assumption of weak nonlinearity, it is fair to assume that at each node, the strength of the fundamental component is much stronger than its harmonics. Hence, in order to find the error voltage VE at the input of the transconductor, it is sufficient to undertake a linear analysis. So, in step 1, we find VE by assuming a perfectly linear transconductor. The superscript 1 refers to the first harmonic component of the signal. Now that we have found VE, we use this information to inject a current proportional to VE cube to model the third order distortion of the transconductor. Note that while doing so, we have desensitized the input. In a practical communication system, the input is a multi-tone signal. To model this effect, we consider two closely spaced tones at omega naught plus minus delta omega. The output naturally has tones at omega naught plus minus delta omega as well. However, the third order distortion of the transconductor also generates intermodulation tones at omega naught plus minus 2 delta omega. These are called output intermodulation component of the third order, or OIM3. To find the strengths of these components, we need to multiply the nonlinear current with the output impedance of the transconductor at omega naught plus minus delta omega, plus minus twice the delta omega. However, if 2 delta omega is much smaller than omega naught, we can make the approximation that the output impedance does not change appreciably within the range of twice delta omega. Hence, the OIM3 components can simply be found by multiplying the nonlinear currents with the output impedance of the loop at omega naught, that is Z0 of omega naught. The multiplication factor of 3/4 appears due to the expansion of the trigonometric identities present in the input tones. It is also noteworthy that as the loop gain decreases, the error voltage VE increases with the frequency and reaches a maximum at the UGB of the loop. Hence, it can be expected that the distortion performance of this transconductor is the worst at the unity gain bandwidth, or the UGB of the loop. For a first order system, this also happens to be the bandwidth of the closed loop system. Keeping this argument in mind, in the rest of the presentation, we will analyze the negative feedback loops around the UGB of the loop. Now let us consider the two-stage Miller compensated op-amp designed for a closed loop gain of k-1 while driving a large capacitive load CL. For a well-designed Miller op-amp, around the UGB of the negative feedback loop, almost all the current from the first stage of the op-amp flows through the compensating capacitor Cc. Also, for large capacitive loads at high frequencies, the effective impedance at the output node is dominated by the load capacitor Cl. Thus, for the purpose of our analysis, we can neglect the output conductances of GM1 and GM2. Also, a well-designed Miller op-amp for large capacitive load requires Cl to be much larger than the compensating capacitor Cc, which in turn will be much larger than the first stage parasitic capacitance C1. With these assumptions in place and noting the presence of a zero cancellation resistor, the loop gain L of S can be expressed as GM1 over S times KCC times 1 by 1 plus SCL over GM2. For a well-behaved stable system, since the loop should behave like a first-order system around the UGB, it follows that the UGB of the loop is GM1 over K times Cc, and the second pole P2 is at GM2 over Cl. From this, it naturally follows that the phase margin of the loop is expressed as shown in the blue box. This is an important expression, and we will refer to this expression again shortly. In order to find the error voltage at the input of the second stage, let us do a linear analysis of this structure. Around the UGB of the loop, since almost all the current from GM1 flows into GM2, it follows that V0 approximately equals to minus GM1 times VE over J omega Cc. From this, it follows that the current through Cl or the load capacitor is Cl over Cc times GM1 times VE in the direction shown in the figure. Note that since Cl is much larger than Cc, this current is much larger than that is arriving through the compensating capacitor. Also, generally, since the feedback resistors are designed not to load the output state significantly, the dominant contributor of the output current is the one that is flowing through Cl. Since this current flows into GM2, this implies that the input voltage of GM2 equals Cl times GM1 times VE over Cc. Recall that this voltage is nothing but K times VE over tan of the phase margin of the loop. This is an important observation, since it implies that the swing at the input of GM2 depends strongly on the negative feedback factor K and the phase margin of the loop. Lower the phase margin of the loop, the larger the swing at this node, and the larger will be the distortion contribution of GM2. Intuitively, this makes sense because if the strength of GM2 is smaller than required, thus implying a poorer phase margin, this will require more swing at the input of GM2 to ensure that the required output current is supplied to the load capacitor. To ensure the distortion of the Miller op-amp in negative feedback, to quantify the distortion of the Miller op-amp in negative feedback, we now desensitize the input and inject the nodes with the appropriate nonlinear currents as shown in the figure. Since INL1, that is the first stage nonlinear current, behaves like the current through GM1, it generates an output voltage of minus G31 times VEQ over J omega Cc. Now, to estimate the effect of INL2, we need to find the output impedance of the loop. The output admittance of the loop comprises of the admittance of the load capacitor Cl, the conductance generated by the feedback around GM2, which is approximately equal to GM2, and the conductance of the feedback resistors. It has already been argued that the feedback resistors do not load GM2 and their effect can be neglected. Now note that below the UGB of the loop, GM2 is larger than Cl. GM2 is larger than omega times Cl, since the second pole is beyond the UGB of the loop. This implies that the output admittance of the loop is approximately equal to GM2, and hence the total output distortion can be found by multiplying the second stage distortion current with 1 over GM2, and its OIM3 can thus be expressed as shown here. Note that the dominant contributor of the distortion around the UGB of the loop in a mirror compensated structure is the second stage, and there is a significant dependence of the phase margin of the loop on the final distortion performance. The lower the phase margin, the larger the distortion. It is worth mentioning at this point that the error voltage VE of the first stage is effectively dependent on the loop gain and the phase margin of the negative feedback loop and is independent of the architecture in question. Hence, we will express the distortion with respect to VE in this study going forward. Now let us look into the distortion performance of a feed-forward op-amp architecture embedded inside the negative feedback loop. Note that this multi-state structure is stabilized by the fast path around through the GM4, which sets the UGB of the loop and ensures a first-order roll-off around the UGB. The top path provides the low frequency gain, and the combination of the two paths with different phase lags produces a zero at the location shown here. Below the zero frequency, the loop gain rolls off at -40 dB per decade, and hence for a well-behaved loop, it is necessary to have the low frequency zero before the UGB. Thus, it implies that the phase margin of the loop can be expressed by the equation shown in the purple box. Like before, we will revert back to this equation shortly. It is noteworthy that since around the UGB of the loop gain is set by the bottom path, the contribution of the current emanating through GM3 to the total output is negligible with respect to that is emanating through GM4. From this argument, it also follows that if both these transconductors have similar distortion characteristics, which is possible if the transistors are biased at similar overdrive voltages, the distortion of GM3 can be neglected when compared to GM4. Thus, the distortion estimation picture now consists of two current sources carrying the distortion currents of GM1 and GM4. The total output voltage can be expressed simply by referring their effect to the output and multiplying the total current by the output impedance of the loop. To find the output admittance of the loop around the UGB, we fall back on the argument that it is the fast path through the GM4 that dominates the signal flow around UGB. Thus, Y0 can be expressed as the sum of j omega CL and the conductance arising out of the feedback around GM4. Note that at the UGB of the loop, omega times CL equals GM4 over K. Thus, Y0 can be expressed as GM4 over K times 1 plus J. After some simple algebraic manipulation, it can be shown that the OIM3 for the feed-forward structure is expressed as this. Note that the dependence of the distortion on the phase margin in this case is much weaker than the case of the Miller compensated op-amp. This is because the second stage of the feed-forward structure is not constrained to supply large currents to the capacitive load, unlike its Miller counterpart. In order to validate the theory, we simulated the Miller and the feed-forward architectures using transistor-level schematics in a standard 130 nanometer CMOS process. The schematic on the left shows the Miller compensated op-amp, while that on the right shows the feed-forward structure. For fair comparison, both of them have been designed for the same bandwidth of 10 MHz. In order to ensure that the input reference noise of both the architectures are identical, we kept GM1 stages identical in both the cases. This plot shows the simulated and the analytical results of the distortion characteristics of the Miller compensated op-amp for different phase margin for a closed loop gain of 4. To generate this plot, we varied the transconductance of the second stage of the Miller op-amp. Note the strong dependence of the distortion with respect to the phase margin of the loop. Also, the simulated and analytical results match within 3 dB of each other. This is the distortion characteristics of the feed-forward op-amp across different phase margins. Note the significantly improved distortion performance of this architecture at lower phase margins and the considerably milder dependence of the distortion characteristics on the same, as expected from the presented analysis. To generate this plot, we varied the first stage compensating capacitor in the feed-forward structure, which in turn varied the phase margin. This plot shows the distortion of the OIM3 plots versus the closed loop gain of the Miller compensated op-amp for a phase margin of 76 degrees, and this shows the same for the feed-forward architecture. Again, note the relatively milder dependence of the feed-forward architecture on the closed loop gain with respect to its Miller counterpart. In conclusion, in this work, we have derived simplified closed-form analytical expressions to estimate the distortion around the band edge of a negative feedback loop, where the distortion performance is the worst, and that the distortion increases with the phase margin of the negative feedback loop and is significantly more sensitive for Miller compensated op-amps than a feed-forward architecture while driving large capacitive loads.